Hello there, Mr. Sutton here, bringing you this lesson on integration by substitution. In this one, we're going to be dealing with definite integrals using this technique. For your warm-up on this one, I'm going to have you just dive right in and try to take this definite integral. So pause the video, give it a shot, and then check your answer on the calculator to see how close you got. All right, so if you got an answer of 20, that is the correct answer. Did you do it the fastest way? Well, I guess we'll find out. There's two different ways to do it. Now, what if you got an answer of 1/4? Well, in that case, I know exactly what you did wrong, and we're not going to have to go too far to see where you went astray. So now follow along, and let's see if we have some matching work here. This is a good candidate for substitution. You might have noticed we have an inner function whose derivative is elsewhere in the problem. So I'm going to start by letting my u value equal 4x cubed minus 1. And then my derivative is du equals 12x squared dx. Dividing by 12x squared to get dx by itself, we get du over that. And now we're going to substitute back in. So we've got 12x squared times u cubed times du over 12x squared. So far, everything is exactly like indefinite integrals. But here's where we reach a crossroads. What do we write for the integral here? The integral symbol. I mean, do we leave it blank? Do we put a 0 and 1 like there was up there? If you copied the 0 and 1, then unfortunately, you've already kind of gone astray. The problem here is that our limits of integration are originally x values because it says dx up here. So that tells us the 0 and the 1 are plugged in for x's at some point. But now you've gone and switched this to a du. So these now should be u values, but instead they are x values. So this is just mathematically incorrect right here, the way it's written. There's two ways around this. One way is to just go ahead and take the indefinite integral and then substitute the x's back in for the u's, plug in the 0 and 1, call it a day. That's probably what you did if you ended up with the answer 20. Another way to do this a little bit faster is to turn your limits of integration into u values. So if I have an x value of 0, well, I have an equation up here that tells me what u is if I know what x is. So u then would be 4 times 0 cubed minus 1, which is to say u would just be negative 1. Now, what if your x value is 1? Well, then you've got 4 times 1 cubed minus 1, which comes out to a u value of 3. So I am going to write most of what I had here, but instead of writing the 0 and the 1, I'm going to write negative 1 and 3 for my limits of integration. And now that I've turned these into u values, I'm just going to go ahead and finish the problem and get u isolated here. So I've got 12x squareds that can cancel, leaving me beautifully with just u cubed du. Taking my antiderivative now, this is going to be 1/4 u to the 4th. And I'm going to put this directly in my evaluation box now with negative 1 and 3, because, again, negative 1 and 3, those are u values. I'm allowed to plug them directly in for this u. So let me go ahead and do that. I've got this 1/4 that's going to get multiplied by the things that are being subtracted. I've got 3 to the 4th, and then I've also got, I'm subtracting negative 1 to the 4th. So this is going to be 81 minus 1, which is 80, and 1/4 of that comes out to 20, just like we got on our calculator. So you were probably pretty close. You just have to substitute the u values in for the x values. So, keeping that last example in mind as a model, pause the video and see if you can find this definite integral. All right, so just like before, I see an inner function whose derivative is elsewhere in the problem. I'm going to let u equal 4x squared plus 4, and then du is going to be 8x dx. Dividing by 8x, I have dx by itself now. And I'm going to substitute back in a moment, but wait, I want to change these x values into u values now. So we've got u equals, if x is 0, u is going to be essentially 0 plus 4, or 4. And if x is 1, then we've got 4 times 1 squared plus 4, which comes out to 8. So what I've got over here now, I have the integral from 4 to 8. I have a 24x over u squared, and I have a du over 8x. So all of that stuff kind of happens at once. And now I can cancel out the 24x and the 8x. That's going to leave me with a 3 up here. And I'm just going to write this as u to the negative 2 du. Bumping up that exponent to a negative 1 and dividing, I've got negative 3 u to the negative 1. And I'm putting that in an evaluation box, evaluating from 4 to 8. So now I've got negative 3. And inside I've got, this is 8 to the negative 1, which is 1/8, minus 4 to the negative 1, or 1/4. Well, this is essentially 1/8 minus 2/8, so that's negative 1/8 times negative 3, which comes out to 3/8. So you might be wondering why I'm having you just make these into u values and not just substitute the x stuff back in and just use x values the whole way through. Well, one of the reasons is because the AP test often likes to have you write things in terms of u and not even bother evaluating it. So that's what we're going to do on this problem, just to get a little bit of practice. Pause the video and see if you can express this whole thing in terms of u, but then don't bother evaluating the integral. All right, so for our u value on this one, I'm going to use 6e to the x as my inner function, because I see a 3e to the x over here. So I've got u equals 6e to the x. Du then is going to be 6e to the x dx. I love taking the derivative of e and the integral. So dividing then, we have du over 6e to the x. And don't forget to get your u values. So if x equals 0, then 6e to the 0, that's really just 6 times 1, which is 6. How about if x equals ln of 2? Well, e to the ln of 2 is just 2, times 6 is going to give us 12. Plugging it all back in now, I've got the integral from 6 to 12 of 3e to the x cosine of u du over 6e to the x. And now the 3e to the x and the 6e to the x can cancel a little bit, so I end up with 1/2 integral from 6 to 12 of cosine of u du. And that's about as far as we have to go on this particular problem, although we could integrate the rest of it and actually get a number for the answer if we wanted. So that's it for definite integrals with substitution. See you later. Till next time, Mr. Sutton signing off.